Right. So this lesson is on chapter 11.0, the periodic table. Now, this is the last part of our syllabus for this year. So let's start. Now, what do we know about the periodic table? Here, it shows us a simplified form of the periodic table. Periodic table is actually a set of elements, a list of elements arranged in order of, how are they arranged? It is increasing proton number. Okay, now what do you mean by increasing proton number? Let's look at the first element in the periodic table. That would be hydrogen, and hydrogen is 1. Helium is 2, and they are both on the first row. Then number 3 is the next row, lithium. And then you have number 4, 5, 6, 7, 8, 9, 10, and so on, 11. And it goes on and on. So therefore, it's arranged in order of proton numbers of all the elements. Now, a horizontal row of element is what we call a period. Whereas a vertical column is called a group. Okay, so which one is a period and which one is a group? So groups are vertical columns. So you have group 1, and what are group 1? It will be these elements. These are group 1. Group 2, all right, and so on. Group 13, group 17. So vertical column, these are called groups. Then how about period? What are the periods? So periods will be the horizontal row. So this will be period 1, hydrogen and helium. Okay, so maybe we should write that down. Can you write down here? Period 1, which is your hydrogen and helium. Then period, so this is your period 1. Then period 2 will be the next row. Okay, period 3 will be the next row. And so on. Okay, so period will be horizontal row, starting with period 1, hydrogen and helium, then 2, period 2, then period 3, and so on. Okay, very messy, so I'm gonna clean it off. Let's see, maybe you can write it in a less messy way. Period 1, which is hydrogen and helium. Okay, period 2, period 3, and so on. Okay, period 1, which is this one. People always forget period 1. Okay, the hydrogen and helium is period 1. Okay, next. On the left hand side, the yellow part, sorry, we have the imaginary line in between metals and non-metals. You have learned this before. Okay, this is an imaginary line which looks like a staircase. Then on the left, the yellow part are the metals. Then on the right, you have the non-metals. And then the green part, which is called metalloids. What is the meaning of metalloids? Metalloids have properties of both metals and non-metals. Okay, they are on either side of the both sides of the dividing line. Okay, that will be called metalloids, the green parts. Now, there's one set that we haven't talked about, and that would be your between group 3 and group 12. This part here, we haven't talked about them yet. All right, so group 3 to group 12, they are what we call the transition metals. So they have a name, they are called the transition metals. But we don't really have to know about them in detail, just know their name is good enough because they are not in our syllabus. These are the transition metals, 3 to 12. Is that okay? Moving down. If I'm going too fast, then you just pause the video. Okay, next one. Now, we need to look more into detail about their electronic configuration. What do you mean by electronic configuration? So in case you've forgotten, right, proton number of lithium is 3, beryllium is 4, boron is 5, etc., etc. And this proton number will tell us the electron structure, electronic configuration. So 3 will become 2, 1, 2, 2, 2, 3, 2, 4, and so on until 2, 8. Okay, so these are the elements of period 2. Period 2. What do you notice about the number 2? Do they have something in common with the electronic configuration? Yes, all right. So period 2 will have 2 electron shells. 2, 1, 2, 2, 2, 3, all 2 numbers only. So 2 shells. Okay, so that's the what a period can tell you. Then how about period 3? How about elements of period 3? Does the number 3 correlate with anything? Yes, again it does. All right. So for example, 11, 12, 13, and so on until 18. If you look at the shells, how many numbers does the electronic configuration have? They are all 3 numbers, right? Which means that they all have 3 shells. They all have 3 shells. So period 3 have 3 electron shells. So we learn our first pattern, right? What's the pattern? The period number tells us the number of electron shells. Okay, period number tells us the number of electron shells. First pattern. Next one. How are elements arranged in the periodic table? So that's what we talked about. Across a period, the number of electron shells an element has is the same as its period number. How about down a group? Now let's go back and look at the same thing. If an element is in the same group, they will have the same what? Okay, what do you mean by same group? That means now it's a column. So now let's look at this one. Okay, That's group 1. Okay, I'm going to rewrite it up because it's getting too messy. Okay, so this is a group. The green one are group 1, group 2, etc., etc. So I'm going to write it down at the bottom here, no space already. So if you look at the group 1, then you'll see that you have lithium 2.1, sodium 2.8.1, and potassium 2.8.8.1. What pattern do we notice which involves the group number? So group 1, all of them have one valence electron. The valence electron means the outermost shell, electrons in the outermost shell. How about group 2? How about group 2? Group 2, you have beryllium 2.2 and then magnesium 2.8.2. What's the correlation? Again, the group number tells you the number of valence electrons. Now let's go to group 13. You have boron 2.3, 2.3, and aluminium 2.8.3. Now, the outermost shell is 3, and this will correlate to the second digit of the group number. It's not 13 electrons, but it's 3 electrons, so the second digit. And last example, group 17. Okay, so fluorine is 2.7, chlorine is 2.8.7. What is the correlation here? Again, the valence shell will correlate to the second digit. Okay, so group number tells you the number of valence electrons. So let's fill in the blanks. Number of same group have the same number of valence electrons. Again, what are valence electrons? Electrons in the outermost shell. Next one, elements in group 1 and 2. So if it is group 1 and 2, they have the same number of valence electrons, the same as the group number. But if they are group 13 to 18, then you have to refer to just the second digit. Okay, for example, group 13 will have 3 electrons. Okay, next, maybe you should highlight it, then it'll be easier to see. Okay, next. If the elements are in the same group, then they will have similar chemical properties. Okay, what are chemical properties? Chemical properties are actually reactions. So they will have similar chemical properties because they have the same number of valence electrons. So the chemical properties depends on the number of, well, not just the number, they must have the same number of valence. How do you spell valence? Oh, E. Same number of valence electrons. Okay, I write the short form for electrons as E with a negative charge, but it's a short form. You cannot write that in exam. All right, short forms are for notes so that we can write faster. Okay, now next. So, similar to what we just talked about, here we are just going to revise. So, we just said that if it is group 1, then they will all have one valence electron. right? Which is shown here, 1, 1, 1. If it is group 17, then they will have 7 valence electrons. Take the second digit. For example, as shown here, 777. Okay, take the second digit. Okay, next. Now, metallic properties across a period. So we talked about the imaginary line that divides the metals from the non-metals. And elements next to this line are called metalloids. So what are the metalloids? As shown in this diagram, the green ones, right? These are the metalloids. So B is boron, Si is silicon, Ge is germanium, As is astatine, and so on. Okay? Okay, now, metals are grouped on the left of the periodic table, and non-metals are on the right of the periodic table. And there is a decrease in metallic properties and an increase in non-metallic properties across a period. That's just a difficult way of saying that as you go across a period, the elements will get less and less metal-like, less and less metal-like. So as you can see here, right, on the left, group 1, 2, 13, things like sodium, magnesium, aluminium, they are metallic. Alright, metallic. Then you hit silicon. Silicon now is a metalloid. Then phosphorus will become non-metal already. So as you go from left to right, the metallic character decreases. It becomes less and less metallic. Okay? So even the nature of the oxides are different. So we have done oxides under the chapter of acid, bases, and salt. Here we have the basic oxide. So to revise, basic oxides are metal oxides. So the metal side, the oxides will be basic. Amphoteric, there are only 3. What are the 3 amphoteric oxides? You have ZNO, PbO, and Al2O3. Zinc oxide, lead oxide, and aluminium oxide. Okay? And then after that, where you have the non-metal oxides, those will be your acidic oxides. Non-metal oxides are acidic. Non-metal oxides are acidic. Okay, so there is a change in the nature of the oxide. As you go from left to right, it's going from basic oxide to amphoteric to acidic. All right, now, what we need to remember is this. How do you classify a metal? Right? A metal can be okay, let me reword that. A metal has a tendency to lose electrons. Okay, to lose electron. Then you classify it as a metal. Example, Na. Na is a metal, it's 281. To be stable, what will it have to do to the 1 in the outermost shell? You must lose it, correct? So that is the metallic character. It will lose 1 electron to become Na plus ion. So it will become 2,8 and becoming a sodium ion. So that classifies it as a metal. Next page. So now we have to talk about the metallic character down a group. Okay, so this is group 1. We are going to use the example of group 1. Can we write down here? This is group 1. Okay. Now, as we go down the group, you notice that the drawing shows us that the size of the atom gets bigger and bigger. Size of atom gets bigger as you go down the group. And also, because of that, there's an increase in metallic property. So that's what we're going to explain. Why will there be an increase in metallic property? Let's write down first. Going down a group, there is an increase in metallic property and a decrease in non-metallic property. Okay, so why does the size of the atom get bigger? We must look at the electron structure. So lithium has an electron structure of 2.1, 2 shells. Sodium is 2.8.1. Oh, now got 3 shells. So of course it will be a bigger atom. How about potassium? It's 2.8.8.1, 4 shells. So even bigger. Alright? So as we go down the group, the atoms get bigger because there are more and more electron shells. What does this do to the attraction between the positive nucleus and the negative valence electron? Right? The valence electron is negative. Hey, why can't I write? Hang on. So the nucleus is positive, the valence electron is negative. Of course, the question is, why is the nucleus positive? Revision. So what does the nucleus consist of? Nucleus consists of protons and neutrons. What charge are protons? Plus charge. Neutrons, no charge. So overall, what charge does the nucleus have? Overall, nucleus is positively charged. Is that okay? So why is the nucleus positively charged? Because it consists of protons and neutrons. Protons are positive. So what keeps the electrons together is that the electrons are attracted to this positive nucleus. Right? Minus and plus, of course, they attract each other. Electrons are minus. Nucleus is plus. So it keeps them there, it holds it there. But as the size of the atom gets bigger and bigger, now the attraction of the negative electron to the positive nucleus will get weaker and weaker. Alright, the electron is further and further away from the nucleus. So the attraction is weaker and weaker, which means that by the time you come to potassium, the electron is lost a lot more easily because the attraction is less strong. Okay, let's fill in the blanks. The size of the atom increases down the group. Correct? Then the valence electron is further away from the attractive force of the nucleus, and therefore it is lost more easily. Okay, more easily. Now, if the electron is lost more easily, that means that it has more metallic character. So this means that, okay, I'm going to draw another arrow down. Lost more easily means what? Means it is more metallic. Okay, if the electron is lost more easily, means that the atom is more metallic. So out of the three, lithium, sodium, potassium, which one is the most metallic? Answer is potassium. Potassium is the most metallic because its electron, its valence electron, is lost more easily. Okay, so let's write out our conclusion. Potassium is the most metallic of the three because its valence electron is lost the most easily. Is that okay? Potassium is the most metallic of the three because its valence electron is lost the most easily. Why is it lost the most easily? Because its valence electron is the furthest away from the nucleus. So it experiences the weakest attractive force compared to the lithium and sodium, the weakest attraction. Okay, and with that, we are done. So, can you now pause the video and try out the test yourself? Pause the video now. After that, I will continue to give you the answers, all right? But you try first. Pause the video. Okay, some basic explanation. So how do you know which element is in group 15 and period 3? I think number 1 is quite easy. You just check your periodic table. Number 2, if it is period 3, it means that it will have 3 electron shells. If it is in group 2, it means that it will have 2 valence electrons. So which one satisfy these 2 criteria? Answer is C. All right, 3 numbers, 3 electron shells, and the outermost shell has 2. Number 3, same group. If they have the same group, then they will have the same charge on their ions. So example, group 1, right, lithium 2, 1, Na 2, 8, 1, K 2, 8, 8, 1. So to be stable, they will all lose 1 electron, which means that they will all lose 1 electron, which means that it will be Li plus, same thing, Na plus, lose 1 electron, and this one also lose 1 electron, so this will be K plus. Okay, next one, similar chemical properties means that they must have same number of valence electrons. So if it is 12, what is the electron structure? 282. So we are looking for something with the last number is 2. which is your 2882. All right, same number of valence electron. Next one, proton number of cesium. You can just check periodic table. Then S13, then how many electron shells? We already say electron shells is shown by same as period number. So you go and check what's the period that cesium atom is in. All right, cesium atom is in period 6. Don't forget hydrogen and helium is period 1. All right, period 1 is hydrogen and helium. Next one, sodium is in group 1. So we are told that sodium is in group 1. So explain why sodium and cesium have similar properties. So you must refer to group 1, meaning that they both have 1 valence electron. No S. Okay? And with that, we are done. That's all.